Okay, I guess we can get started. So Tuesday is our exam. It'll cover everything from the beginning of the semester through whatever we get through today. The test will have a range of questions. I'll have a certain percentage that should be gimmies. You know, if you've been here, been paying attention, should be pretty simple. I'll have some that will really focus on the concepts in class. Maybe a couple that have you do should not be a complex, it should be a simple calculation, and then you'll go from there and answer a question or two. And then I will try to put on a question or two that will challenge everybody. I don't believe in tricky questions. I don't think tricky is what I'm after. I really care about what you know, and I care about what everybody knows. So I'll have enough questions so that hopefully you can all show me what you've picked up this semester, and a couple of questions for those that really understand things well to, show me just how deep your understanding really is. So again, my goal is not to make this tricky. It's not to make it difficult, but I do want to challenge everybody. You're college students. You're up for it. So with that in mind, the questions will be probably mostly short answer. Maybe a calculation or two. You shouldn't have to write essays on this. They should be short, simple, to the point. We'll do a few notes today, and then I'll leave some time at the end of the class for you guys to ask me any questions that you have about anything so far. Do you have questions on the exam or the format of the exam? So for those of you taking it in class, just show up with something to write with and bring a calculator. That's all you should know. If there are equations or numbers or constants that you need to have to answer the questions, I will provide those. I don't expect you to memorize a list of things, so shouldn't be a lot of memorization involved, but understand the concepts. For those of you who have been here, you know what I've focused on so far, and I will try to restrict my questions to those concepts that I spent a fair bit of time talking about. For those doing it at home, you'll have to log on to a Zoom invitation that I send you. Once you do that, I will email you the exam. You can then either write the exam out on a piece of paper, take pictures of it, email me back. You can write it out on a Word document. Just have some way of sending me your answers. I don't care what format they're in as long as I can do it. You need to keep your Zoom meeting up at all times until you've finished the test and emailed it back to me. So if you have any questions over the weekend, I'll have my email, I'll have my computer. I can hopefully help you guys all out. Any questions so far? Okay, let's just do a little bit of new material on soils, and then I'll let you answer some or ask some questions about the exam at the end if you have any. Okay, so let's review a few terms. These are things you've seen already, and this will probably be helpful for the exam as well. We talked about some physical constants the other day. Remember, force is mass times acceleration. Physicists measure that in units called newtons. Kilogram meter per second squared. Stress is when you apply that force over an area. The units that we use for pressure are pascals. Can also be written as newtons per meter squared, or if you really write the whole thing out, it's kilogram meter per second squared. So pascals are a unit of stress or pressure. We have several types of stress. We have compression, where the stress is applied in a squeezing manner. We have tension, which is where the stress is applied in equal and opposite directions, pulling things apart. And then we have shear, where objects are pushed into opposite directions. And all of these types of stress occur in the earth, and rocks and soils respond to each of these types of stress a little differently. We mentioned before that rocks are really strong under compression, but only about 1/10 as strong under tension. So it's much easier to pry a rock apart than it is to crush it. And shear falls somewhere in the middle of those two. Remember, rocks always bend before they break. This is something we'll talk about a little more a little bit later in the semester. And as we just mentioned, most geologic materials are very strong under compression, very weak under tension. Okay, so again, force is mostly due to the Earth's gravity pulling down things that have mass. Force is mass times acceleration. And then stress is that force divided by the area that it's applied over. So force divided by area. Okay, we went through all this last class, so I'm going to jump ahead a little bit. Okay, so we talked about stress. When things are put under stress, they can deform. And the way that engineers and physicists measure the amount of deformation under stress is with a unit called strain. Strain is the change in length over original length. I used a few examples. If you had a rod that's 1 meter long and you put it under tension and it's 1.1 meters long after, the change in length is 0.1 meters. The original length is 1 meter. 0.1 meters over 1 meter is 0.1. The units cancel out. So it's what we call a dimensionless variable, and you can think of it as a percentage or as a fraction. In that example I just gave you, the fraction would be 0.1 and the percentage would be 10%. Now for soils, we're going to talk a bit about strain rate, how fast the materials deform when they're placed under stress. And it's the strain divided by time. Since strain is dimensionless and time has units of seconds, strain rate has a unit of per second. Seems a little weird, but you can think of it as a fraction per second or a percentage per second. Okay, this next one's a new one for you. And again, I just mentioned it to get you to think about how materials respond when humans mess around with them. And this one's called Poisson's ratio. It's a ratio of thickening to thinning when you squish something. So let's say we have this little wedge of, we'll just say it's rock, okay? It's a wafer of rock. And we're going to squish it, okay? Just like me pressing down on the tabletop up here. Or maybe even better, think about if I had a little cube of clay or silly putty or something, and I push down on it. What's it going to do? It's going to spread out, right? So when you compress something in one direction, what you tend to do is smush stuff out, that's a real scientific term, on the sides. But different materials squish out differently. want you to think about the units for Poisson's ratio. So it's the thickening, how much it widens, over how much it thins in the direction it's being squished. So let's say we squish this by 1 centimeter. We make it 1 centimeter thinner. And in the process, the edges squish out or thicken by 0.1 centimeters. So the ratio of thickening to thinning would be 0.1 centimeters divided by 1 centimeter. What's the unit? Centimeters divided by centimeters. It's another one of these dimensionless units. So again, think of it as a percentage. So in this case, it widens by like 0.1 or about 10%. So it's a dimensionless variable, just like strain is. Most geologic materials, rocks, soils, have Poisson's ratios that are 0.1 to 0.4. So if it's 0.1, you squish it by 1 centimeter, the edges squish out by 0.1 centimeter. But there is one really weird rock that doesn't behave like all the others. And it has a Poisson's ratio that's negative 0.1. If a Poisson's ratio is negative, what does that mean? When you squish it, what happens? Yeah, see those little yellow arrows? They actually go the opposite way. When you squish it, it contracts. That seems impossible, doesn't it? Doesn't it seem odd that you'd squish something down and it would pull in on the sides? This happens very rarely. There's only one rock type I know that does it, and it's a sandstone. Not all sandstones do this, but some sandstones do this. I'm going to try to draw this with my finger because I forgot my cool pen today. But think of sand grains as being like little tiny silicon balls, okay? So we're just going to make some little sand grains. This is not going to work, is it? Well, let me do this. All right, let's see. We have a row of sand grains. Oh, this is terrible. Yeah, that's not working. Okay, I'm just going to have to do it on the board behind me. People at home, sorry about this, but go away. Okay, so let's say we had some sand grains that are packed together in these nice rows where one row sits directly on top of the sand grains from the underlying rows. Now, if you squish this, do you think this is the tightest arrangement of sand grains I can get? No, what sometimes will happen is a whole row of these will shift like half a grain. And what will happen is then you end up with sand grains that now are in their tightest possible configuration. And when that happens, you reduce the volume and it contracts in from all sides. Now think about it. Let's say you build a house or some sort of heavy structure on some sandstone. The weight of the house is going to push down on the sandstone, right? Now, if this sandstone beneath the house has a negative Poisson's ratio, then this rock beneath the house is going to contract, isn't it? But this rock out here is not, right? It's not being squished by a house. So what happens, this pulls in, what sort of, if this rock here stays in place and this rock pulls in under the house, what kind of stress do you have right on the edge of your house? You have compression here, right? But since this is pulling apart here, this is going to be tension right on the edge here, because this stays in place and this pulls inward. So right on the edge of your foundation, you have tension. And what did we say about how strong rocks are under tension? Not strong at all. Do you want cracks in rock right alongside your house? Rains on your house, that water sheds down, you can get water that gets in here as well. And then all sorts of problems can occur after that. So again, this is just one of these things to get you to think about how rocks respond when we mess with them. You think, oh, simple, I'll just put a house on some soil and, you know, like everybody else does. But it really matters what the properties are of the material that you build these structures on. Most of the time they're stable, but every once in a while they are not. All right, enough physics for a while. Let's just talk a little about soils conceptually. Like I mentioned a couple classes ago, soils are a big deal in environmental science. Most environmental science degrees require a course on soils. Some of the bigger universities have entire degrees that are focused on soils. This is kind of the interface between the human and the geologic world. And a lot of human activities greatly impact our soils. Soils are what plants grow in. So soils affect plant cover greatly. Change the nature of the soils and you'll change the way things can grow in them. The next chapter we're going to do is on groundwater. Groundwater becomes more important to humans every day as we burn through our supplies of surface water. And now we're extracting groundwater at a rate that's not sustainable. So we have to recharge these groundwater stores. But in order to recharge groundwater, rainwater has to make its way through soils, down into the ground, and eventually into the rock. So soils hugely affect the recharge of groundwater. Right now we've got a couple of huge fires raging up in the mountains from us. One thing they've noticed that fires do, they strip away the plant cover, right? So the thought by scientists for years is that whenever we have fires, that'll actually be good for groundwater because it should allow water to soak into the ground better because, you know, the plants aren't there to take any water away. But what they found out is that isn't true. What happens is that the soil gets burned by the fire as well, and it creates some new little molecules called colloids that actually prevent water from soaking into the ground. It's almost like making pavement. So not only are we going to strip away the plant cover up there, but a lot of times that means that we're going to increase the runoff. not as much water will soak into the ground. And now we have all this loose soil up there and ash and tree fragments, and we're going to have more runoff. So what that ends up doing is it greatly affects the amount of sediment that goes into the stream. The Poudre River is likely to be impacted by this fire for several years with more sediment from more runoff. That's going to affect the fish population. There's going to be all sorts of effects that we're going to feel downstream because of it. And it's just due to how the soils respond to fire as well. As we're going to see, not this class, but next Thursday after we come back from the first exam, we're going to look at the strength and stability of soils based on how much water can get into them, so that we can assess whether structures we build on soil will be stable or not. Some soils are remarkably stable. They're great to build things in. Some things are terrible to build things in. They have very little strength, or the strength changes abruptly when you add water or disturb it. These are things we'll talk about next week. Okay, let's talk about what a soil is. Anybody in here have lots of experience with soils? A job you've had in the past? Most people don't have much experience with soils. Your experience might be growing a garden. You know, maybe you dug up some dirt and grew something in it. And if you ask most people, what's a soil, they're going to tell you, it's dirt. It's the dirt that sits on top of the rock. And you know what? That's a perfectly fine definition. But for understanding how humans interact with the geologic world, we're going to need a definition that is a little more workable. So like I said, maybe the simplest definition is dirt, any loose surface material. But if you look closely at that dirt, you're going to see that it's not all the same stuff. There's some rock fragments. Some are big, some are small. There might be some clay in there. There might be some salt deposits in there, especially out here in the west where we get lots of evaporation. You can see lots of salts forming in your soil. And sometimes those salts actually cement together all that loose material. You can get organic debris in there. Remember, plants grow in soil. So when the plants go through their life cycle of living and then dying, that dead material gets incorporated into the soil. And then you have things that live in the soil. You have microbes, you have bugs, you have worms, you have burrowing mammals. All sorts of stuff live in the soil. And then the plants that grow in the soil send roots down. What do plant roots do? They do pretty much three things. What's the purpose of a root of a plant? What does it do? Sucks up water. What else? What's that?
Provides stability.
Provides stability. Yep. The other thing, it sucks up nutrients. Has to have nutrients to survive. So that's kind of the three things it does. Okay? So you've got an awful lot going on in the soil. And then, so far, we've only talked about the dirt, the rock particles, the broken down plant particles, but there's also moisture in your soils. There's water in your soils. Sometimes a lot, depending on what kind of climate you have. How close is it to a river? Has it just rained or snowed? How long has it been since it rained or snowed? So it could be really dry or really wet. If it's dry, what's going to be in the spaces between the rock fragments, the dead plant material. It's air, right? But it can be more than just air. Those plants are breaking down, right? And when plants decay, they can give off gases. And then sometimes people spill stuff onto the ground. We spill petroleum products, and sometimes that gets into the soil. So the soils have solids, they have liquids, they have gases, they have living organisms, different percentages of all this different stuff. So soils can be really different depending on where you are and what their history has been. Now, if you ask a farmer what a soil is, he might have a very different definition than what an engineer has. If you have a big pile of sand, just sand, a farmer isn't going to be too thrilled about that as a soil. It doesn't have nutrients, not really good to grow anything on. In fact, most farmers won't even call that a soil. A soil is something you can grow something in, something you can till. But to an engineer, when they see all that loose dirt, they'll say, you bet that's a soil. So we have definitions that vary by discipline sometimes too. So farmers, it's something to grow something in or something tillable. A slightly more scientific definition might be any loose surface material from rock weathering and or organic matter. And that material could be solid, liquid, or gas. As I mentioned before, and this just kind of puts it on a slide, soils can be pretty complex. A soil that's forming out here in Greeley, Colorado in a semi-arid, sagebrush-covered environment is really different than something you might get in northern Wisconsin. Very different than something you'd get in northern Canada, and completely different than something you'd get in a tropical rainforest. Different rocks in those areas, different plant cover in those areas, different precipitation in those areas, different levels of human interference in those areas. And all of those things can affect the development of a soil, how fertile it is, how stable it is for building things in. So we have solids, mostly broken up rock. Organics, basically dead plant material. You can have gases or vapors. You get air from the atmosphere that gets in between these solid particles. You can get gases released from deep geologic processes that are making their way up to the surface. You can get gases from the soil itself as those organics break down. Sometimes you can get water that starts to evaporate within your soil. And then it can have liquids, mostly organics, or mostly water, but sometimes you can get organic liquids. Or people can be stupid and spill paint thinner, paint, alcohol, petroleum products. So again, it's more than just dirt. That dirt is pretty complex. Okay, this is one of the more important things I think we'll discuss, because it really gives you an idea of how soils behave and how they evolve over time. And this is something called soil horizons, or it's basically layering within a soil. Now, most of you said you really don't have any up close and personal experience with soils. And if you did grow a garden, chances are you use something that we call topsoil, right? You've heard of topsoil. This is kind of an organic, rich, fertile material that's scraped off the top of some area that has a lot of soil so that you can bring it and make a garden out of it. But most natural soils have real distinct layers if you dig through them. And we'll talk about these layers individually and then see how they vary from place to place based on climate, interaction with humans, and so on. So the first horizon, and this is kind of from the Earth's surface down. So this is the stuff that's right on top. So if you stick a shovel into the ground, this is the stuff you're going to hit first. This is the O horizon. O for organic. It is a layer of soil that consists mostly of dying, dead, decomposing plant material. So you get the plants that are growing in the soil, they live, they die, and when they die, their plant fibers get incorporated back into the ground in this uppermost layer. And if you've watched plants decay, it tends to be black or dark brown. So it tends to be a dark, organic, rich zone of decomposing plant material. Now out here in the west, the arid west, we have crappy O horizons. In fact, most places don't even have a good O horizon. If you go to a rainforest where you have plants that are living and dying at a rate that's much greater than what we have around here, you might get a really thick O horizon. Sometimes several feet thick. And you can go to places like peat bogs where you've got sort of swampy, marshy conditions, and you have so much plant material that you can get several feet of this stuff. In fact, so much so that eventually it'll be compressed into something called peat and then later coal. So the O horizon can vary from basically nothing in desert environments where there's very little to no plant growth to several feet or meters thick in swampy, marshy areas. So right beneath this, generally, at some depth, you then start getting mixing with your O horizon and the weathered rock material from below. And that's called the A horizon. Now, in a real simple world, which pretty much doesn't exist, you would think, okay, we've got this O horizon on top, right? It's where all the dead stuff is. And then we have a layer of eroded rock, okay? And in the middle, they're sort of going to mix together. And that's all going to sit on some bedrock. So you think, oh, there's probably going to be maybe 3 horizons, right? We're going to have an O horizon, all organics. We're going to have a zone where they mix together. And then the bottom, we're going to have mostly rock material. It would be that way if it wasn't for our good friend water. Water then sort of mixes up those 3 zones and gives us the next 2 zones. So as it rains, rain lands on the soil. Some of it runs off into streams and rivers, but some of it soaks down through the soil. And as it soaks down through the soil, remember, water has that polar covalent bond. So it has those strong dipoles, those strong attractions. And as it goes through the soil, what it's going to do is it's going to grab on to molecules and atoms that are also polar. And it's going to pull it with it as it goes down. That process where water grabs onto things in the soil and moves them is something called leaching. So right below the A horizon, we get something called the E horizon, also referred to as the zone of leaching. And this is part of the soil where water carries around these charged ions, these charged organics. We call them mobile because they have a strong charge that can grab onto the moving water, and the water can move or leach it away. So it moves away a lot of the nutrients that a plant would use. And it leaves behind things that aren't easily leached. Two things that aren't easily leached are iron and aluminum. And what happens over time is that iron and aluminum interact with the gases in the soil. And one of the primary gases in the soil is oxygen. And what happens when you oxidize iron? What do you get? Rust. What color is rust? Red. Aluminum. When you oxidize aluminum, you get another kind of rust. It's an aluminum oxide, and it tends to be orange. So this zone of leaching tends to be a red-orange, nutrient-depleted zone in your soil. And it's nutrient depleted because the water picked up all this material and carried it downward. So the next layer below is where all of that leached material ends up. And it's called the zone of accumulation. Now coming up in lab, and we're not going to do much with lab this week. I'm trying to get you guys a little farther along before we start our geologic maps and then soils maps. So don't worry about labs this week with the exam coming up, but we'll get into geologic maps next week, and then we're going to get into soil maps. And a couple terms you might see for the zone of accumulation are argillic soils. Argillic just means clay. Clay is important when it comes to building things. It's something we're going to talk about later. So if you have argillic clays, those are going to be concerning to you if you want to build structures in a particular area. We also have carbonate. CaCO3, I don't care if you remember that or not, but it's just another term where you get a lot of accumulation of calcium. Okay, so we have our organic zone where all the plants are accumulating. Get down deep enough, it mixes with rock, but as water moves through it, it's going to leach away some of the nutrients and leave behind sort of this dead zone in your soil called the E horizon, or zone of leaching. And as the water moves down, it will eventually interact with the rock in a way that it will sort of spit these nutrients back into the soil, into this B horizon, zone of accumulation. Below that is your C horizon, and that's pretty much just broken up rock. And then the last horizon isn't really soil, it's the rock that's everything sits on. So these are the 6 main horizons. Their presence, the degree to which they develop, how thick they are, is all going to be a function of climate, plant growth, human interference. So what I want to do is take a few minutes and talk about how climate affects us, and take a look at what these soils actually look like out in nature. Any questions on this so far? Okay. Looks like you're caught up on your notes. Okay, so if you go to different places, these soil horizons are going to be developed differently. In some places, you might have a really thick E horizon, zone of leaching. In other places, you might not. Think about that E horizon, that zone of leaching. What do you need to form a zone of leaching? Water. So do you expect much of a zone of leaching in arid environments? Where would you expect lots of a big E horizon? Keep her on land. What land environment would you expect lots of leaching to occur in? You need lots of water, right? You need lots of rain. Rainforest would be an area where you have a lot of zone of leaching. So climate is probably the main determinant because it determines how much water you have over long periods of time, which dictates plant growth. It also dictates how much water will be infiltrating into your soil, the temperature and the plants and the amount of water determine how quickly rocks will break down. Because remember, at the core of this, soil is rock material and dead plant stuff. As far as the solid components are concerned. So climate has a huge effect on how these soil horizons develop. The type of rock that the soil develops into. Different rocks have different chemistries, which means that the soils that you derive from these different rocks will be different, all other things being equal. A rock forming on sandstone is going to have a much different nutrient portfolio than a soil forming over an igneous rock or a carbonate rock or any other rock. They all have different chemistries, so the chemistry of your soil is going to be different, and the nutrient makeup of your soil will vary according to the rocks that are underneath. One chapter I don't know if we're going to get into in here, I cover it in my other classes, is relationships between geology and your health. And some soils worldwide are very iodine poor. Different rocks have different iodine levels. Okay? There is a disease called goiter. I don't know if any of you have seen goiter. It is a disease of the thyroid where basically you get a tumorous lump that develops on your neck. It looks like you swallowed a basketball. It's a horrible disease, but it's caused by a lack of iodine. And about 100 years ago in the US, North Dakota, parts of Montana, South Dakota, parts of Minnesota were known as the goiter belt. Have you guys ever seen anybody with goiter? You have? Where'd you see it? Yeah, you can find it on the internet, but have you actually ever seen a human being walk around with it? I used to live up there, and I had never seen anybody with goiter. That's because we got rid of it. We got rid of goiter. And goiter is caused by an iodine deficiency. And it's because the rocks up there don't have any iodine in it. You guys know how we solved it? I know one person knows how we solved it. We put iodine in something that everybody uses, salt. You've heard of iodized salt? That was the birth of iodized salt, was because northern soils were so iodine poor, we put iodine in something that everybody uses. Yeah. You can find pictures. It's not hard. Yeah.
So they developed this because of the lack of...
Yeah, it was so prominent in the northern tier states. They're like, how do we get everybody iodine supplements? Well, it's easy. You just put it in salt because it's tasteless, it's colorless, it doesn't do anything. So you go to the store now and most of the salt is iodized. But now we get our food from all over the place too. Back 100 years ago, everybody that lived up there got their food from up there. They didn't go to Safeway. You know, they went to the local markets where all the plants were grown in the same iodine poor soil, so nobody got iodine. Now it wouldn't be a problem. We could probably get rid of iodized salt today, because where do you get your food from? You go to the grocery store. You get an avocado from Ecuador. That probably has iodine in it. You get lettuce from California. You get tomatoes from Texas. You get citrus from Florida and Arizona. You get stuff from all over, so you're getting nutrients from all over. But in the past, we used to eat locally. There's a push now to eat locally again, right? It's not without problems, because you don't get the trace elements. You don't get these nutrients from all over the place like we have been. Yeah. You can get too much. I'll definitely cover this then. You guys seem interested in it, so I'll cover it. You've seen it, but yeah, you can get too much, and then that can become toxic. So yeah, we'll go into this a little later in the semester. Slope. We've been talking about stress and strain, and I've been showing you stress from stuff sitting on a slope. Well, when you have soil on a slope, where does it want to move? Downhill, right? And that's the problem we're going to have after these fires, is that you strip away the plants. Those roots provide not only a stable platform for the plant, but it holds the soil together too. Take all that plant material away, put the soil on a slope, put rain or snow on it, and it's going to start washing away. So when you have soil sitting on a slope, they may not be able to develop as long and as thoroughly as soils that are in flatter areas. There's one other main determinant when it comes to the thickness and development of soil horizon that I don't have listed here yet. It's probably not terribly obvious. Can you think of anything else that would affect how these soil layers develop that I don't have listed?
Is it like building houses or like human population?
One would be human disturbance. Yep, because humans can come in and we can scrape away all the soil in a day with the right earth moving equipment, right? So humans disturb soils all the time. So that's one. What if humans don't disturb it? The factor that I'm thinking of is time. The longer you have, the more these soil horizons can develop and separate themselves from others. So young soils, very different than old soils. And you get young soils where maybe you had a natural or a human disturbance, forcing them to sort of restart. Okay, I'm going to give you two examples and then we'll call it quits. So we're going to look at two climates. See how quick we go, maybe three. So this first climate would be considered to be cool wet. So kind of this could be eastern United States. It could be a place like the Pacific Northwest. It's not tropical, but it gets a fair bit of rain. So we would consider that to be a cool, wet climate. Now we're going to think about how this climate's going to affect soil. And since soils have organics, we'll think about how it affects plant life as well. So are we going to have organics? Yeah. You go to eastern US, Pacific Northwest, lots of stuff grows. Now you don't have the production like you do in the tropics because the temperatures aren't quite as high. Growing seasons aren't year-round. But you definitely get a lot of plant growth. It's warm enough and it's wet enough. So you have good organic generations, which means you'll have a good organic zone and you'll have a good A horizon. Remember, the A horizon is the mixture of organics and weathered rock material. So you should have good O and A horizons. What about leaching? Would you expect some leaching? Yeah, because it's wet. So not only will you have an E horizon, you'll also have your B horizon, your zone of leaching and your zone of accumulation. And remember, in your E horizon, most of the nutrients get washed away, but aluminum and iron stay behind. Then they oxidize and they turn orange-red. And then that material moves down, and at some greater depth it drops this material and forms clays or carbonates. So you get a good you get a good O horizon, good amount of organics. You get a good A horizon, organics mixing with rocks. You have enough water movement to get a good E horizon. If you get a good E horizon, you should also get a good B horizon. And pretty much everywhere you're going to have C and R. You're obviously going to have rock at some point. And if you have rock, you're probably going to have weathered rock sitting on top. So in this environment, you get it all. This is a great environment for creating all of the different horizons we talked about. I don't care if you know this term, but something that might come up, especially if you go farther in geology. We call these pedalfer soils. Ped is kind of the science word for soil. Al for aluminum, kind of signifying that zone of leaching. So these are called pedalfer soils. I don't use the term, but in case you see it somewhere, that's the origin of it. Okay, there is a picture of a pedalfer soil. Maybe not all of it, okay? Do you see the O horizon? Where's the O horizon? It's right at the top, right? Let me see if I can. So it's right up in there. You don't see any rock fragments, right? You just see black. That's like the top soil, okay? And then here's your, so that's the O horizon. You notice here you've got black material mixed with rock fragments, right? What horizon would that be? That's your A. Notice the color of this horizon. Kind of that orangey, right? So that's your zone of leaching. So that's your E horizon. And then you see this sort of light brown material right here that generally signifies lots of clays. So that's your zone of accumulation. That's your B horizon. So you're not seeing your C and your R, but you're seeing the top four layers right there. So the O is just organics. The A is organics mixed with rock fragments, and you can see that there. Dark material with some white rock fragments. Your E has lots of aluminum, maybe some iron. It oxidizes, gives you that yellow, orange, reddish color. And then B is where the nutrients that are pulled out of the E layer accumulate, form clays, and give you the B horizon. If you went down farther, you'd see some rock fragments, and then you'd see solid rock. So that's what a good stratified, well-developed soil horizon soil looks like. Now this one's kind of my favorite one to talk about because it's like the last one on steroids. So this is going to be a warm, wet climate. This is your tropical rainforest. So it's wet, it's going to have lots of water. It's also warm. So what does that do to plant life? You get a lot of plant life. You go to the tropics, jungle, right? Lots of plant life. So that means what for organics? Just a ridiculous amount of organics. So you have super thick O and A horizons. What's generally below the A horizon? E. Would you expect a big zone of leaching? Yeah, because you get so much rainfall, you get a ridiculous zone of leaching. Sometimes meters thick, completely devoid of nutrients. So what are the plants going to do? Okay, think about this for a minute, right? So plants send down roots. What do the roots do? We talked about it a minute ago. They're looking for what? Water, stability, and nutrients, right? Now you can find water throughout the soil, and you can have stability throughout the soil. What about the nutrients, though? So the roots go down, right, from the surface. They can find nutrients in the O horizon. They can find nutrients in the A horizon. But then what if you had a zone of leaching that was meters thick? Are there nutrients there for the plants? Are they going to send their roots and just sort of start looking for stuff? No, so what happens in tropical environments is the roots go down in the O, go in the A, they start to go into the E and they can't get their nutrients, so instead of going deeper, they branch out sideways. So what you have are very broad, shallow root systems in tropical areas. The roots don't go deep because there aren't nutrients in that massive zone of leaching. So in many ways, these plants are just living off of the remains of their dead brothers and sisters. That's where the nutrients are coming from. And because of the high temperatures, the remaining aluminum and iron oxidizes even faster. Reactions speed up when you have higher temperatures. So with the increased water infiltration and the increased oxidation, you get these super extensive zones of leaching. And they're kind of like a dead zone. What happens if you strip away the plant life in a rainforest? Do you have any way of rejuvenating your O horizon if you strip away the plants? No, so that upper layer erodes very quick. What do you get then if you erode the organics? Pretty soon you're in that zone of leaching, right? Will anything grow in the zone of leaching? Not easily. So when we deforest an area that has these massive E horizons, plant regeneration is really, really slow. So the deforestation that occurs down in places like the Amazon, once they strip away all that organic material, it doesn't come back very quick. That upper layer is pretty thin, and then the stuff that below it is pretty much leached out. It's kind of a dead zone. So you see lots of this red and orange rich soil, and that sort of signifies a zone that plants are going to have a really hard time sending their roots into, because plants won't waste energy putting roots into nutrient poor soils. think I have a picture of this coming up here. Then we can just finish out. If you have your E horizon, you also have a B horizon, and you always have your C and R as well. All right, I'll let you finish your notes and I'll show you a picture of this. I think the photo I have coming up is of a sugar cane farm in Brazil. I'm not positive of that, but I think that's where I got it. And just think in your mind what you'd expect to see if you dug through this. And actually what I have is an area along a road where they dug down into the soil. Okay? So what should you see up on top of the soil? You see lots of organics, right? And then what are you going to see under the organics in the A horizon, which also has organics? This huge zone of leaching, right? Which should be red-orange. Well, okay, these are called laterite soils. Again, I don't care if you remember that. So don't even bother writing it down. There you go. Yeah, that red stuff is very nutrient poor. You get a thin layer. You can see it up near the top. Like right in here, you do get some dark material. But yeah, you would think, oh, these soils should be super fertile, right? They're in this area where you get lots of plant growth. Well, the plants are just growing in that upper few inches to feet of the soil. This stuff down here, pretty dead, pretty devoid of nutrients. And that's because they get so much rainfall that it's dragging the nutrients from that level down farther. If you were to dig farther, you'd eventually find your B zone, which will have lots of clay in it. And yeah, if you strip the plants off of this, then there's no way really to generate or regenerate the upper part of the soil with nutrients, because the nutrients are actually coming from the dying plants. Okay, so let's finish with that.